Hey there, welcome to The Explainer. You ever wonder how your favorite streaming service remembers exactly where you left off in a show? Or how an online store keeps your shopping cart perfect, even when you close the tab? Well, it's not magic. It's databases. And today, we're going to pull back the curtain on the simple, surprisingly elegant blueprint that organizes, well, pretty much our entire digital world. So, to get our heads around this, let's start with a classic problem. Let's imagine we're building a brand new digital system for our local library. We've got books, we've got members, and we've got all the loans happening. How in the world do we keep track of all that without it turning into a total mess? This simple library challenge is honestly the perfect way to understand the fundamentals of how every database really works. Okay, so the very first step in our little library project is to understand the single most important building block of any relational database. And here's the good news, it's something you're probably already super familiar with. Now, the official kind of fancy term for it is a relation. But don't let that word scare you, it is just a table. That's it. A simple grid, the rows are for individual things like one specific book, and the columns are for its properties, like the title and the author. So using this structure, we can make a books table. See? Each row is one unique book in our whole collection, and the columns, book ID, title, author, they give us the specific details about it. This clean, simple grid, this is the foundation for everything else we're about to build. Now, to make sure our tables don't get all chaotic, they have to follow a few simple rules of the road. Every table and every column needs its own unique name. You can only stick one piece of information in each little cell, and this one's really important. No two rows can be exact clones of each other. These rules make sure our data is always predictable and totally reliable. So having these nice organized tables is great, but how do we guarantee that we can find the exact book or the exact library member we're looking for every single time? Well, for that, we're going to need a few more rules. To find anything reliably, you need a unique ID for it, right? Kind of like your own library card number. In the database world, we find this perfect ID in 3 little steps. First, we look for any super key. That's just any mix of columns that makes a row unique. Then we whittle that down to a candidate key by finding the smallest possible combination that still works. And finally, we just pick one of those candidates to be the official primary key. For our books table, that's easy. It's just the book ID. Okay, this is where it gets really, really cool. How do we connect a book to the person who borrowed it? We do it with a foreign key. Imagine we've got a loans table. Inside it, we'd have a column called, say, borrower ID. That ID isn't just a random number. It's a foreign key that points directly to a specific person in our members table. It's literally the glue that lets us create relationships between all our different tables. And to make sure this whole system never, ever breaks, we have 2 unbreakable rules. Entity integrity just means the primary key can't be blank. Every single book has to have its ID. And referential integrity means a foreign key has to point to something that actually exists. You can't check out a book to a library member who isn't even in the system. These rules are basically the database's built-in error prevention. Okay, so we've got our building blocks and we've got our rules. But listen, you wouldn't build a house without a blueprint, and you definitely don't build a database without one either. It is time to plan out our library system visually. We do this with something called entity relationship modeling, or just ER modeling for short. It's basically a simple way to draw a map of our data. This way, everyone, from the librarians to the programmers, can get on the same page and agree on what we need to track and how it all connects, all before a single line of code gets written. An ER model really just has 3 core parts. Entities are the main nouns, the things we care about, like a book or a member. Attributes are the adjectives, the properties of those things, like a book's title or a member's name. And relationships, those are the verbs. They describe how these things interact. For instance, a member borrows a book. Simple as that. The final piece of our plan is something called multiplicity. Again, fancy word, simple idea. This is just how we define the library's real-world rules right inside our design. For example, can one member borrow many books? Yep, that's what we call a one-to-many relationship. Defining these rules makes sure our database actually works the way the library does. All right, our plan is solid. Now it is time for one of the most important, but honestly often overlooked steps in designing a database, the cleanup. We need to refine our blueprint to make it as lean and efficient as possible. So you might be asking yourself, why not just dump everything into one giant table? I mean, if a member borrows 3 books, why not just list all 3 in a single cell called borrowed books? Well, that approach, my friends, leads to absolute chaos. Think about it. What happens when a member's address changes? You might have to update it in 10 different places, and if you miss just one, boom, your data is now inconsistent and wrong. The solution to this mess is a process called normalization. Honestly, the best way to think of it is like the Marie Kondo method, but for data. It's a technique for tidying up our tables by breaking them down into smaller, more logical pieces. The whole point is to get rid of repetitive information and prevent those kinds of update errors from ever happening.
Normalization happens in stages, or what we call normal forms. The first one, 1NF, is super simple. Every cell can only hold a single value. That means no stuffing a list of 3 book titles into one little box. The next steps, 2NF and 3NF, handle more subtle issues. They're all about making sure every piece of information in a table really truly belongs there and depends entirely on that table's primary key. It just prevents a whole class of weird errors down the road.
So, why do we go through all this trouble? Is it worth it? Absolutely. Because a normalized database is incredibly efficient. When a member's address changes, you update it in exactly one spot. This makes the whole system way easier to maintain, it's way less likely to have errors, and it saves a surprising amount of storage space. We've designed our blueprint, we've set up the rules, and we've cleaned everything up. There is just one last piece to the puzzle. How do we actually talk to our database? How do we ask it questions and give it commands? We do that with a language called SQL, which stands for Structured Query Language. You've probably heard of it. It is the universal standard language for pretty much all relational databases. It doesn't matter if you're working with our little library database or a massive system for a global company, chances are you're going to be using SQL to talk to it. Now, SQL is really like 2 languages in one. First, you've got DDL, the data definition language. Think of this as the architect, the one who designs the whole database structure, the building itself. Then you have DML, the data manipulation language. This is the librarian, the one who actually works with the data inside that structure, putting books on shelves and finding them again. And that librarian's language, DML, really boils down to 4 core actions. Select lets us find data, like asking, hey, find me all the books by Jane Austen. Insert adds new stuff, like a new library member. Update changes data that's already there. And delete, well, it removes it. Almost everything you do with a database comes down to these 4 simple commands. But the real power of SQL comes from asking more complex questions. What if we want a list of which members have which books? For that, we use a join to combine information from our members and loans tables. An inner join would show us only the members who currently have a book out, but an outer join could show us all the members and just list the book they have checked out, if they have one. It's how we connect the dots across our whole system. And that's it. From simple tables all the way to the SQL language, you now know the fundamental blueprint that powers everything from a library catalog to the most complex apps on your phone. It's all just about creating order from chaos. So now that you know the plan, what system would you design? Thanks for joining the explanation.